Zwiebach from the MIT, who will discuss recent progress in open string field theory.
Thank you very much. It's great to be here. Thanks to the organizing committee for this really charming and memorable hospitality that is making this week a really pleasant and lovely experience. I'm grateful to be able to talk about this work, one of a group of people that has been trying to make progress with open string field theory and, in fact, analytic progress. So, from the years 1999 to 2003, evidence accumulated through numerical solutions that, in fact, open string field theory had solutions that, starting with constructing the string field theory on one background, you could see backgrounds that were quite far away. And that's really what we wanted a string field theory for. So the evidence was strong at that time, though numerical, that you could see the tachyon vacuum background starting from a D-brane background. You could see, starting with a D-brane background, lower codimension branes. And you could see backgrounds related by marginal deformations, even large marginal deformations. That situation was fun and exciting for a couple of years, but became frustrating as the ability to do all this analytically was absolutely limited, and there were no solutions. So we were relieved by this misery, by Martin Schnabel, who in November, a year and a half ago, found the analytic solution for the tachyon vacuum. And part of my aim here is to explain in some simple terms, in terms of pictures, why the simplicity or what really changed. And as usual, developments are triggered by simple observations, a change of picture, and suddenly all kinds of things that were difficult become easy. So let me remind you first of the usual strip frame, in which we have a local coordinate psi for an open string that comes from time minus infinity in radial quantization. At time equals 0, we have a half circle, the left half of the open string, the right half of the open string. With the usual map Z log psi, one maps to a strip, and this is called the strip frame of an open string. You see the boundary of the open string over here, and the various open strings coming from infinity here. The left half and right half of the open strings are there. You see them at time equals 0. If you consider the operator L0, which is radial growth in psi coordinates over here, amounts to changing the length of the strip by a little bit. But there is another frame that is very peculiar at first sight, is the Sliver frame. Sliver is a name for a projector of the star algebra, and this projector was discovered around 2001, 2002, and it's as a projector, it's an element that squares to itself, and it's based on a conformal map from psi coordinates to another one, which is the Sliver frame. And now it's really upside down with respect to this completely. The boundary of the world sheet is just here, a little piece of the real line, and the left and half parts of the strings go all the way to infinity, with the midpoint, in fact, at infinity. And the map that does that is the inverse tangent, and this is the z coordinate, so you see the evolution of the strings here. Well, using this frame is what made all the difference. Now, you can see here that what would be a simple deformation here is an L0 deformation in the Z frame, which is a dilation that sort of keeps the vertical left and right part of the strings vertical. And that corresponds to a more complicated transformation here. That's, if you do the conformal map of the operator L0 defined here over there, you see a series of Virasor operators. Ln Virasor operators refer to the psi frame. L0 is simple here, but this curly L0 that we'll call L It's simple here, but it's complicated there, but this is the operator that will be important. So just the same way, the anti-ghost zero mode in that same frame, what you would construct in this way, is this operator B, and that's the Schnabel gauge requiring that the field satisfies this condition. Moreover, the ingredients in any of these solutions are what one would call dressed surface states. A surface state is a disk with a local coordinate here in which you insert test states. So the surface state is defined by the overlap with test states. So you compute the correlator with the test state mapped here and all the other operators that may be sitting here as part of your correlator, and that defines a state that you compute with a correlator. So we will be showing pictures in which the only thing you need to know is that you're getting states, and you should see a picture of a local coordinate that always will be a sliver. So the tachyon vacuum solution of Schnabel is constructed with these states psi alpha. So what are they? So the local coordinate is this part. That's where you insert the test state to get the overlap. And then you have a length alpha here, and this line is identified with this. This geometry we call a wedge state geometry. You insert a ghost here, and a line integral of the anti-ghost over there. That's the state psi alpha. Then the solution, the complete solution, is written in terms of derivatives of this psi alpha, summed, and an extra piece called the phantom piece. It's actually, while this is simple, the fact that this is needed is very subtle and not fully understood geometrically why it's needed. In fact, this part that would be ordinary, that we call the ordinary piece, is enough to make the equation of motion hold against any test Fock state. But this piece that we call the phantom piece, a name, I'm not sure it's good, but certainly this term you don't see in the level expansion. If you do the level expansion, take the limit as n goes to infinity, you just don't see it, but nevertheless is needed for the solution to hold strongly, as demonstrated by Okawa, Fuchs, and Kreuter. So this solution was presented last year in strings, and there's been some developments this year. That's what I mainly want to talk. First, understanding the meaning of this special choice of sliver frames and what's really going on, how much freedom you have in doing this. So that's one. Now, two is a solution for marginal deformations that I will present in some detail. The things in red I will present in some detail, and the things in blue in a little less detail. So this solution was obtained by Schnabel and our group at MIT as well. Then there's been some work in doing things for the superstring as well. And Erler was the first who got this started, and Okawa, they've completed solutions for marginal deformations of the superstring. Then these are called regular marginal deformations. Those are deformations generated by operators, marginal operators with essentially vanishing OPE. And an extension to more general deformations for one case was figured out by Fuchs, Kreuter, and Potting, and Fuchs and Kreuter, and Kiermaier and Okawa. Kiermaier is an MIT student, are going to write a paper that will appear soon. Finally, I will talk about Offshell amplitudes. So the key structure of these solutions are wedge states, as you've seen in the solution that I drew. So these are states, surface states. Here's the local coordinate where you insert a state to test, and this is state wedge alpha. You think of this as the left part or right part of the string, the left part of the string. So actually these are like left and right because these are identified. And the star product of open string theory combines left and right in a simple way that puts them together. So the product of this state W alpha with W beta is W of alpha plus beta. The state in which alpha goes to 0 It's an identity state. It's called the identity element of the star algebra. So there's interesting things happening here. Just like for B, the zero mode of the Virasoro operators, the one that dilates things in the z-plane, where the sliver sits, it's a linear combination of operators. It's important to consider also the BPZ conjugate, which has negatively moded Virasoro operators, and something very special happens. The commutator of L with L star is L plus L star. It's a very simple thing. It's very difficult to achieve this, but in general happens for certain projectors that we've called special projectors. It's not always true. At any rate, this operator L plus, which is the sum of them, plays a very important role in the theory. As any operator is defined by a contour integral of a vector field times the stress tensor, can be separated into a left part, integrating half of the string, and a right part. But the special thing about this L plus is that the left and the right parts commute. And that's because the real vector field for L plus vanishes at the midpoint. As a result, you can look at what L plus is, and it's actually very simple. It's the insertion of the stress tensor integrated over Z. So this is the generator of translations in the z-plane, only acting on the left part of the string. So if you have a wedge, it will move one part of the wedge and will make it bigger. That's why you have a formula that the wedge state of length alpha is obtained with L plus acting on the identity. Associated with L plus, there is the corresponding anti-Gauss insertion, and those are operators that will be important for us. Now, was the sliver very important to get a solution? Was that really necessary or not? In fact, it was not really necessary, but it's the simplest thing you can do in order to compute states, say, in a level expansion. The idea is that any surface state can be mapped into each other by a reparameterization that preserves the midpoint. The surface state is really this surface, and here's the open string. Here's the local coordinate, and you can map psi to psi prime by preserving A, Q, and B, the ends of the open string and the midpoint. So this map by Riemann's theorem certainly always exists. So it's possible to map conformally any two surface states, and in fact you can map any two projectors. So there used to be this projector that was in some ways simpler than the sliver, called the butterfly projector. And the shape of this curve over here for the local coordinate was never all that obvious what it was, but actually now we know. If you just square this line, you obtain the vertical line. So these two projectors, butterfly and sliver, are clearly related. If you have a wedge state with a map z squared on this side, you can map a wedge state to a funny state of the butterfly, and just like these states multiply nicely, the butterfly states defined this way multiply nicely. So you have a family of states like the wedges, and everything goes through. In fact, you can also do another deformation. If you have a sliver, you can reparameterize it without changing it by this map. It will keep those vertical lines, but it will affect the size of a wedge. So in this way you can deform the Schnabel solution. It's an interesting non-trivial deformation. So in fact you have two kinds of things you can do. You can choose a different projector, and once you choose a projector you can do a beta deformation that changes the solution and gives you other cases. So there's a lot more freedom, and the conclusion is that these things are basically projector-based gauges, and you can use whichever you want. So let me describe a new solution that was found around end of January, and this solution is in fact the simplest solution of open string field theory. It's simpler than the Schnabel solution. It should have been found first, but that's not the way it worked, of course. So what do you have? We consider a dimension 1 matter primary, and therefore form a state that is BRST closed by the usual procedure. We try to construct a marginal deformation by constructing corrections in the power series on the marginal parameter, and this equation of motion gives you a set of equations to solve. At every order, you must solve an equation of the form cube psi n equals phi n, which phi is built by the lower psi's. You certainly need that psi n be BRST exact. It's guaranteed to be closed, and if you're really working with an exactly marginal operator, it will be, in fact, exact. Otherwise, you wouldn't have a solution. Now, I should remark that people, of course, tried to solve this before, and what you would do is work in the Siegel gauge, in which you use the propagator, Siegel gauge propagator that builds strips. So a solution, say to fifth order on the marginal deformation, would be based on this string diagram, and unfortunately, you cannot go very far, because all these string diagrams are essentially impossible to do the conformal map to the upper half plane. And so if you want to calculate the solution, you need this conformal map in closed form, and those maps cannot be done. In fact, Giddings and Martinek were the ones that did the one for the 4-point function. It was a tour de force. So let's try the new gauge. In the new gauge, you would have this string field that satisfies, that is in the Schnabel gauge and satisfy the corresponding Virasoro condition, and you may try to calculate minus b over L to solve for psi 2. Well, this can be calculated, and the answer is quite simple. So let me show you the solution to second order. So it's a state. Here you take the tests, and you put a CV at 1, a CV a distance t away, and you integrate from t equals 0 to t equal 1. In between, there is this anti-ghost insertion that we discussed before, just integrating the anti-ghost. So that's the second order deformation. It's a very simple thing. If you want to test that it works, you act with a BRST operator. The BRST operator has nothing to do with a CV. Another CV just concentrates in B, produces an L. L, as I told you, generates deformations of the length of the wedges, so it's a total derivative in t, and you get two terms, one when t is equal to 1, which corresponds to the star product that you really wanted to solve, and one when t is equal to 0, that you need this limit to vanish. Well, the generalization is actually remarkably simple, and that's a very nice thing. So the generalization is shown here with several moduli integrations, CVs, CVs, and B insertions. So the simplicity here is that this is a cylinder, and you can map it immediately to the upper half plane and can calculate whatever you want. So in fact, for the very interesting case of a rolling tachyon, we have the fabulous coincidence that this is a regular vertex operator, so you can use the solution and you can calculate now exactly the rolling tachyon. So we have the full string field theory solution for all fields, so all levels, anything you want to ask about the rolling tachyon solution. And it's all reduced to integrals of closed form expressions, now elliptic functions or inverse elliptic functions, and they're quite calculable. The tachyon itself continues to do this puzzling effect of oscillating in ever larger amplitudes. The series appears to be completely, absolutely convergent, but it's not very clear yet what the meaning of this solution is, and I don't think it will become terribly clear until we understand better how to calculate observables. Nevertheless, there's been interesting possible interpretations discussed by Elwood and by these authors as well, but we still, I don't think it's very clear what this solution means, but we know it's the exact solution. If you have singular OPEs for the marginal operators in general, it becomes more difficult to find a solution, but nevertheless it seems that it's possible now. A very interesting case of this marginal deformation that has a singular OPE was done by these authors, and Kiermaier and Okawa are going to present very soon a solution based on some clever idea of using two solutions that are complex conjugated of each other and a gauge parameter that relates them in such a way that the real solution is obtained by a gauge transformation with square root of u. So we'll be seeing this paper in a couple of weeks, I believe. Okay, I want to finish my talk basically by discussing Offshell amplitudes, something we've been playing with Leonardo Rastelli, and there's a nice paper as well by this Japanese group from Sapporo University. Now, the first surprise is, unless you think for a little while, the propagator is not just B over L. It can't be, actually, and was noted by Schnabel early on. It's a little more complicated. It's a very unusual structure if you think about it, but this is what you need to invert the kinetic term on the gauge slice. The problem is that the projector to the slice, which is BC, where C is some ghost operator, this projector is not BPZ conjugate invariant. So the kinetic term has a P star, so you have to invert something like this. In the Siegel gauge, this was simple because B and B star were the same, so this became L0 very quickly. Here it doesn't happen. So actually you have this structure of the propagator, and as far as I can tell, this makes the Offshell amplitudes absolutely interesting and totally different from what we're accustomed. So the aim of what we're trying to do is develop pictures to do the Feynman rules and understand the most puzzling aspect of this thing, which is that if you use Schwinger parameters, you seem to have two Schwinger parameters for every line. And we know physically we should just have one. So suppose you try to compute the 4-point amplitude. You can take the propagator, which is in this form, and commute q to the right. You would have the piece that you would say it's familiar, and an unfamiliar piece over here. So if you're computing a 4-string amplitude, you have the familiar string diagram, and the less familiar one with two modular parameters. So in order to understand how to evaluate these things or develop general Feynman rules, you should learn to see what B over L does and B star over L star does on star products. And here is a couple of pictures. B over L on the star product of two states sort of shrinks them over a distance t, inserts an anti-ghost insertion, produces an extra piece of world sheet, and integrates from 0 to 1 only. If you do this B star over L star, it actually blows up the states into big strips of width S. The modular parameter is not the length of a strip anymore, it's the width of our new strips, and adds little pieces over here and integrates from 1 to infinity. So here is the Offshell part, the first part of the Offshell Veneziano formula. Now, while in the Siegel gauge people wrote expressions for the Offshell Veneziano formula, they involve the inverse of complicated elliptic functions. So the nice thing is that we have now very simple formulas for the Offshell amplitudes, formulas you can stare at and try to figure out what they satisfy. And here is the Feynman diagram. Here are states 1 and 2. There are states here 3 and 4 shrunk to a distance t from 0 to 1, and little extra pieces over here, 1/2, 1 minus t. This corresponds to, this is a cylinder, so you can imagine the states over here with separations 1, 1, 1, and t, and you can calculate the modular parameter. Here is the answer, actually, and it's the familiar formula multiplied by an Offshell extension that takes this interesting form, and all the terms vanish when p squared is, each tachyon is on shell. Interestingly, this formula produces half of the moduli space. You should go from 0 to 1, And the full formula is not obtained by just analytically extending this to an integral from 0 to 1, but you must calculate the t-channel diagram. This formula actually would break down at lambda equal 3/4, which is a sign. We're integrating from 0 to 1. Even if you would let t go from 0 to infinity, you would not cover moduli space. In fact, when t goes to infinity, if you think a little bit about the picture, you will realize that gets to lambda equal 3/4. That's quite a factor here. At any rate, that's what you get. Now, how about the other part of the diagram? This second piece over here, the unusual one. You have Q acting on states. Well, this is really quite strange, but perfectly okay as far as we can tell. There's the state cube psi 3 here, for example, one diagram. Of course, if psi 3 is on shell, this would vanish. But here you have two modular parameters, S1 and S2, and you overcount moduli space. So this is very different. Offshell amplitudes in all the gauges we were familiar were just, you have the moduli space, you put local coordinates at the punctures to go off shell, and you integrate over a section. Here you don't, apparently. You have the moduli space, but you integrate over something that covers many times, and sometimes covers with an extra continuous integral, but those extra coverings, in many cases at least, they're related to things that are cube size, so the external states. These whole terms would vanish if you are on shell. It's very different the way on shell and off shell works here. So actually there's interesting things about asking how the factorization works off shell as well here, and we hope to report on that soon. Even if you are on shell and you go to the 5-point function, this whole propagator, you can move the Q because you're near to external states here and you just left with B over L, or you can move the Q to the other side. But by the time you have 6 lines, the full propagator with two modular parameters must lie on a line. And again, it doesn't seem you get covering of modular space in the strict sense, but you overcount a bit, but you get the right amplitudes as well. We hope to get some time to loop amplitudes, but there's a real puzzle here. So let me show you geometrically what has happened. If you think in Siegel gauge, you had a strip between states 1, 2, 3, and 4. And here is on this strip, there is the midpoint of that strip, that it's a line. What has happened in Schnabel gauge is that states 1 and 2 have become sectors of a pizza, 4 and 3 are sectors of a pizza, and at least in one of the terms you get two extra sides. The propagator sort of acts on the left and on the right, but the whole middle line has been collapsed to a point. So if you go to a one-loop diagram, you're going to encounter at least an apparent difficulty, and we don't know if it's a serious one. But if you have an internal line like this, if the midline collapses, actually the string diagram already goes to the closed string pole degeneration. So it's not all that obvious how you're going to get all the moduli. So we don't know, but we hope this will be a very interesting clue as to the behavior of closed strings in this gauge and how we get the observables. So I'm really done at this moment. I want to say the Schnabel gauge is now recognized to be a projector gauge, very different from Siegel gauge. Deformations by marginal operators are really simple. Some progress for the superstring, some understanding of the Offshell amplitudes. And nevertheless, it seems clear that at least the lessons of the development have not yet been fully absorbed. The tachyon vacuum for the superstring has not yet been found. There are several groups, including some here, that are working on this problem. The same for the lump solutions, or D-branes as solitons. Of course, some more sophisticated solutions may be instantons in the superstrings or monopoles. And finally, once you had the Siegel gauge for the open strings, it was relatively simple to find the analog gauge for the closed strings. And I don't think we have any idea yet at this moment what is the analog closed string of that, but we hope it will exist. Thank you.
Thank you. Questions?
So the Schnabel gauge, there are exact states which satisfy the Schnabel gauge. So how does that affect the perturbation theory?
Well, we certainly have the Schnabel gauge is peculiar in that there are some exact states that satisfy the gauge conditions, something that didn't happen in the Siegel gauge. So we're not seeing any effect of that yet in the perturbative amplitude. So if it has a problem, maybe will arise at loops or some issues of Offshell factorization. So we haven't seen that effect yet, but it could be an interesting complication.
More questions? Okay, if not, let's thank Barton again.